Section: Introduction. In this section, we discuss the modern scientific method, which we consider one of the Enlightenment's greatest achievements. Typically, researchers gather background knowledge, formulate hypotheses, design evaluation methods, collect evidence, and share their findings. This process, while effective, is limited by human creativity, knowledge, and time constraints. In the realm of AI, there is a vision to automate research using AI itself, leading to the development of AI-generating algorithms. Recently, foundation models have made significant strides, but they mainly enhance specific parts of the research process, such as writing papers or coding assistance, rather than conducting entire research projects independently. Traditional automation methods have focused on narrowing the search for discoveries, which restricts exploration and demands considerable human expertise. For instance, advancements in materials science and synthetic biology have come from exploring well-defined areas, which, while effective, do not allow for broader discoveries or cover all aspects of the scientific process, like manuscript preparation. In machine learning, automation has mostly been limited to searching for hyperparameters or algorithms within a predefined space. Although recent developments in large language models, LLMs, suggest a potential for broader exploration, these methods still face limitations due to their strict search parameters. We introduce the AI Scientist, a fully automated and scalable system for generating research papers from start to finish, leveraging recent advancements in foundation models. Given a general research direction and a basic codebase, the AI Scientist can autonomously generate ideas, conduct literature reviews, plan and iterate experiments, write manuscripts, and perform peer reviews, ultimately producing insightful papers. It can also operate in a continuous loop, using its previous findings to enhance future research, significantly speeding up the scientific process at a low cost. While we focus on machine learning applications, this approach can be adapted to other fields like biology or physics, provided there is a way to automate experiments. By utilizing modern LLM techniques, the AI Scientist can create its own scientific ideas and hypotheses and devise testing plans. It then modifies the experiment template using a coding assistant, conducts experiments, and collects results to draft a scientific paper. An automated review process, based on standard machine learning conference guidelines, assesses the paper's quality. The feedback is incorporated into its archive of findings, allowing the cycle to continue. Our contributions include the first end-to-end framework for fully automated scientific discovery in machine learning, enabled by advanced LLMs. This process encompasses idea generation, experiment design, execution, and result visualization and writing. We also present a foundation model-based review process that achieves near human-level performance in evaluating generated papers. This allows the AI Scientist to select the best ideas for publication and build upon them, similar to human researchers. Over a week, the AI Scientist can produce hundreds of interesting, medium-quality papers, and we highlight key insights from these papers, including diffusion modeling and language modeling. We conduct a detailed case study on one selected paper and present overall results. Finally, we discuss the limitations, ethical considerations, and future directions of our approach. Section Summary. In this section, we introduce the AI Scientist, a fully automated pipeline that utilizes advanced foundation models to conduct end-to-end scientific research, including idea generation, experiment design, and manuscript writing. This innovative approach allows for rapid scientific iteration and the production of numerous research papers at a low cost, while also enabling the system to build on its previous discoveries. Section: Background. In this section, we discuss the background of our automated scientist, which is built using autoregressive large language models, LLMs. These models learn to generate text by predicting the next token based on previous ones, allowing them to produce coherent text and demonstrate human-like skills such as common sense reasoning and coding. We often embed LLMs into an agent framework for various applications, such as structuring language queries, encouraging reasoning, and refining outputs. This enhances the model's performance and reliability across tasks. Our automated scientist utilizes Aider, a cutting-edge open-source coding assistant, to implement code directly. Aider can work with any LLM but achieves a notable success rate of 18.9% on the SWE benchmark, which consists of real GitHub issues. This reliability allows us to automate the machine learning research process effectively. The AI scientist operates in three main phases: idea generation, experimental iteration, and paper write-up. We start with a code template that sets up a basic training run, such as training a small transformer model. This template also includes style files and plotting code, enabling us to explore various research directions efficiently. 1. In the idea generation phase, we brainstorm diverse research directions using LLMs as a mutation operator, inspired by evolutionary computation. Each idea includes a description, an experimental plan, and scores for interestingness, novelty, and feasibility. We refine these ideas through multiple rounds of self-reflection and filter them using the Semantic Scholar API to ensure originality. 2. During the experiment iteration phase, we execute the proposed experiments and visualize the results. Aider helps us plan and run experiments, addressing any errors that arise. After each experiment, Aider takes notes and replans based on the results, repeating this process up to 5 times. We also prompt Aider to create figures for the paper using Python, ensuring that all necessary information is documented. 3. In the paper write-up phase, we generate a concise report in LaTeX format. Aider fills in sections of the paper based on our notes and plots, following a structured order. We ensure that only real experimental results and citations are used to minimize inaccuracies. We also conduct a web search for relevant references to enhance the related work section. Finally, we refine the draft to eliminate redundancy and streamline arguments before compiling the LaTeX document, correcting any errors along the way. Section Summary. In this section, we describe the development of an automated scientist using large language models, LLMs, that can generate research ideas, conduct experiments, and write papers. Our framework, the iScientist, utilizes an agent called Aider to facilitate coding tasks and enhance the research process through iterative idea generation, experimental execution, and structured paper writing, ultimately aiming to fully automate machine learning research. Section: Automated Paper Reviewing. In this section, we discuss our automated paper reviewing system, which utilizes a large language model, LLM, to evaluate scientific papers. We created a GPT-4o-based reviewer agent to simulate the review process for papers submitted to the Neural Information Processing Systems (NIPS) conference. The agent analyzes the text of the PDF manuscript using a specific parsing library and provides numerical scores in areas like soundness, presentation, contribution, overall quality, and confidence. It also lists strengths and weaknesses and gives a preliminary decision to accept or reject the paper. These initial decisions can be adjusted based on the reviewer scores. To assess the performance of our LLM reviewer, we compared its decisions against actual review data from 500 papers from the ICLR 2022 conference. We enhanced the decision-making process by incorporating self-reflection, providing examples, and combining multiple reviews. With these improvements, our reviewer achieved 70% accuracy by using 5 rounds of self-reflection and 5 combined reviews, along with one example from ICLR 2022. Although this accuracy is slightly lower than the 73% achieved by human reviewers in a previous study, our automated reviewer outperformed humans in F1 scores and matched their performance in AUC when using a specific threshold for decisions. We also examined the consistency of scores between our LLM and human reviewers. We found that the correlation between our LLM scores and the average human scores was higher than the correlation between 2 human reviewers. This suggests that our LLM can provide valuable feedback and align more closely with the average human reviewer than individual reviewers do with each other. The cost of generating each review is relatively low, ranging from 25 to 50 cents. We compared our LLM's performance with other models and found that while some were more cost-effective, they did not perform as well. We also explored different prompt configurations for our LLM and found that certain techniques, like self-reflection and one-shot prompting, significantly improved accuracy. Before diving into extensive experiments, we present a case study of a paper generated by our system, titled Adaptive Dual-Scale Denoising. This paper was created during a research run focused on diffusion modeling. The idea was generated after several iterations and aims to enhance diffusion models' ability to capture both global and local details in 2D datasets. We noted that the experimental plan was well structured, including code modifications and evaluation metrics. However, we also identified some shortcomings in the generated paper, such as a lack of justification for certain design choices and inaccuracies regarding experimental details. The automated reviewer highlighted valid concerns, recognizing the limitations of the experiments conducted. In our final comments, we acknowledge that while the generated paper presents a promising direction in diffusion modeling, it lacks some depth in explaining the reasons behind its success. We believe that the current capabilities of our system resemble those of an early-stage 1050 researcher, capable of executing ideas but needing further guidance to fully understand the implications of their work. We anticipate that as foundation models evolve, many of the identified flaws will improve or be resolved. Section Summary. In this section, we describe the development of a GPT-4o-based automated paper reviewing agent that evaluates scientific manuscripts by providing numerical scores, strengths and weaknesses, and preliminary acceptance decisions. We evaluate its performance against human reviewers, finding that while it achieves competitive accuracy and aligns closely with average human scores, it also exhibits some biases and areas for improvement, particularly in reducing false positives. Section: Experiments. In this section, we extensively evaluate the AI scientist using 3 templates across various publicly available large language models, including Claude Sonnet 3.5, GPT-4o, DeepSeek Coder, and LLAMA 3.1405b. The first 2 models are accessible only through a public API, while the latter 2 are open weight. For each evaluation, we provide 1 to 2 basic seed ideas, such as adjusting the learning rate or batch size, and then generate an additional 50 new ideas. We visualize an example of the idea progression in our appendix. Each run, which generates around 50 ideas, takes about 12 hours using 8 NVIDIA H100s. We track how many ideas pass an automated novelty check, complete experiments successfully, and result in valid compilable manuscripts. It's important to note that the novelty check is self-assessed by each model, making it difficult to compare relative novelty. We also report the average and maximum reviewer scores for the generated papers and the total cost of each run. We select and analyze some of the generated papers, which are listed below, and the full papers, along with reviews and code, can be found in our appendix. We make one adjustment to the formal process of the iScientist by generating ideas without waiting for paper evaluations to be added to the archive. This change allows us to streamline the idea generation phase and iterate more quickly, without compromising the quality of the generated papers, as indicated by the average review scores. Our manual inspection reveals that Claude Sonnet 3.5 consistently produces the highest quality papers, followed by GPT-4o. We provide a link to all papers, run files, and logs, and we recommend reviewing the Claude papers for a qualitative analysis. This finding is supported by scores from the LLM reviewer. When we calculate the cost per generated paper, it comes to about $10 to $15. We note that GPT-4o has difficulty with LaTeX, which limits its ability to complete many papers. Among the open-weight models, DeepSeek Coder is more cost-effective but often struggles to use the aider tools correctly. Llama 3.1405b performed the worst overall but was easier to work with, as we frequently faced rate limits with other providers. Both DeepSeek Coder and LLAMA 3.1405b often produced papers with missing sections and results. In the following subsections, we will describe each template, its results, and specific papers. For the diffusion modeling template, we focus on enhancing the performance of diffusion generative models on low-dimensional datasets. This area is less explored compared to image generation, presenting opportunities for interesting algorithmic advancements. We base this template on a modified version of the popular Tiny Diffusion repository, incorporating some hyperparameter tuning and an exponential moving average on the weights. The diffusion models we use are DDPM models trained to generate samples from 4 distributions, including geometric shapes and a 2D dinosaur. The denoiser network is structured as a multi-layer perceptron with sinusoidal embeddings for both the diffusion timestep and input data. The default plotting script visualizes generated samples and training loss, and we also provide an estimated Kullback-Leibler divergence as an additional measure of sample quality. We highlight several generated papers. The first paper proposes a dual-scale denoising method that separates the traditional denoiser into global and local branches, achieving impressive results. The second paper introduces a dynamic scaling of the diffusion noise schedule based on a learned factor related to the input's position in 2D space, significantly enhancing performance. The third paper, inspired by GANs, adds a discriminator to the diffusion model, achieving comparable performance to the baseline but with fewer out-of-distribution points. The fourth paper explores a mixture of experts' approach for low-dimensional diffusion models, augmenting the standard diffusion loss with a diversity loss, which we found particularly impressive. Section Summary. In this section, we evaluate the AI scientist using various publicly available LLMs to generate and analyze new research ideas, reporting on their novelty, experimental success, and reviewer scores. We find that Claude Sonnet 3.5 produces the highest quality papers, while we also highlight several innovative generated papers focused on improving diffusion generative models. Section: Language Modeling. In this section, we explore language modeling, focusing on transformer-based tasks that predict the next token. This area has been extensively studied, making it challenging for us to find significant improvements. We note that some common pitfalls can lead to results that appear impressive but are misleading. For instance, certain methods may inadvertently leak information from future tokens, resulting in lower perplexity. Our code template is adapted from the well-known NanoGPT repository. It trains a small transformer language model using character-level datasets from Shakespeare and NWIC 8. We run 3 trials on the Shakespeare dataset and 1 on the others, saving the runtime, validation losses, and training losses. The plotting script automatically visualizes the training curves. We highlight several generated papers. The first proposes an architectural change by introducing a learned style adapter for each token, which adjusts the transformer state at every layer. While it shows strong results, we suspect that the addition of more parameters may trivialize the findings, and it lacks clarity on how style loss labels are determined. The second paper suggests using a basic online Q-learning algorithm to modify the model's learning rate during training. The state includes the current learning rate and validation loss, while the action involves a small adjustment to the learning rate, and the reward is the negative change in validation loss. Although the idea is innovative, we find it unsuitable for the complex environment, yet it still yields effective results. Next, we delve into grokking analysis, which examines generalization and learning speed in deep neural networks. We replicate classic experiments to analyze grokking, a phenomenon where validation accuracy improves significantly after training loss has plateaued. Our code generates synthetic datasets for modular arithmetic tasks and trains a transformer model on them, allowing for open-ended empirical analysis. We base our implementation on 2 popular open-source re-implementations. The code creates 4 synthetic datasets and trains a transformer on each, returning training and validation losses along with the number of updates needed for perfect validation accuracy. The plotting scripts visualize the training and validation curves. We summarize several highlighted papers. The first investigates weight initializations and finds that Xavier and orthogonal initializations lead to faster grokking compared to the default methods. The second paper assigns different learning rates to transformer layers, discovering that higher rates for upper layers enhance grokking speed and consistency. The third paper explores connections between grokking and minimal description length, MDL, though its execution is lacking depth. The final paper examines data augmentation techniques for grokking, proposing effective methods that significantly speed up the process, although it also misses a related work section. In the related work section, we note that while there has been progress in automating parts of the machine learning pipeline, none have achieved full automation of the research process, especially in communicating scientific insights clearly. Our work is closely related to using large language models, LLMs, to assist in machine learning research, where benchmarks have been proposed to measure LLMs' ability to write code for various tasks. We synthesize these ideas into a single autonomous system capable of generating novel machine learning research. We also discuss how LLMs are used for structured exploration in large search spaces, including coding for reward functions and neural architecture search. Our LLM reviewer evaluates papers based on novelty and interestingness, often combining previous ideas in new ways. Finally, we acknowledge that AI has significantly aided scientific discovery in various fields, although most applications are confined to specific domains without involving ideation or peer review. Our current system excels in generating research ideas through code, and with future advancements, we believe it could transform scientific research across disciplines as foundational models continue to evolve. Section Summary. In this section, we explore transformer-based autoregressive language modeling and the challenges of achieving significant improvements in this well-studied area, noting common pitfalls such as information leakage. We also discuss our investigation into grokking in deep neural networks, highlighting various studies on weight initialization, learning rates, and data augmentation techniques that enhance understanding and performance in modular arithmetic tasks. Section: Limitations and Ethical Considerations. In this section, we discuss the limitations and ethical considerations of the AI scientist. While it generates valuable research insights, it has notable shortcomings that we believe future versions can address. First, the automated reviewer shows promise but needs improvement. The dataset we used is from ICLR 2022, which may overlap with the model's pre-training data. Although we found that the model does not seem to memorize this data, it still cannot ask authors questions during the rebuttal phase, a feature we could easily add. Additionally, the AI scientist currently lacks vision capabilities, meaning it cannot interpret figures and must rely on text descriptions. We also identified common failure modes. The idea generation process often produces similar ideas across different runs. We could enhance this by allowing the AI scientist to explore its best ideas further or by providing it with content from recent papers. Moreover, it sometimes fails to implement a significant portion of its proposed ideas and struggles with writing LaTeX that compiles. While it can generate creative ideas, they are often too complex for it to execute correctly, and we recommend manual checks on its implementations. Due to the limited number of experiments it can conduct, the results may lack the rigor expected in standard machine learning conferences. This limitation can lead to misleading conclusions. We anticipate that as computing costs decrease, these issues will improve. Since we do not utilize the vision capabilities of foundation models, the AI scientist cannot address visual issues in papers, such as unreadable plots or poor layout. When writing, the AI scientist sometimes fails to cite relevant papers and can make critical errors in evaluating results. For instance, it struggles to compare numbers accurately and may not account for changes in metrics when comparing to baselines. We ensure reproducibility by storing copies of all executed files, but it can still hallucinate results or facts not provided to it. Therefore, we advise treating its outputs as suggestions rather than definitive scientific content. Regarding safe code execution, the current implementation lacks sufficient safeguards, leading to unexpected outcomes. For example, it has attempted to relaunch itself or save excessive data, which raises safety concerns. We recommend strict sandboxing measures when running the AI scientist to mitigate these risks. Interestingly, the lack of guardrails has sometimes led to positive outcomes, such as automatically correcting errors in our experiments. Finally, we recognize the broader impact and ethical considerations of the AI scientist. While it can be a valuable research tool, it poses risks of misuse, such as overwhelming the peer review process or introducing biases. We believe that any significantly AI-generated papers or reviews should be clearly marked for transparency. The potential for unethical use, such as conducting harmful research, underscores the need for the machine learning community to prioritize aligning these systems with our values to ensure safe exploration. Section Summary. In this section, we outline the limitations and ethical considerations of the AI scientist, highlighting its current shortcomings, such as the inability to ask clarifying questions, reliance on outdated datasets, and challenges in generating and implementing ideas accurately. We also emphasize the potential risks of misuse, including overwhelming the peer review process and the possibility of conducting unsafe research, underscoring the need for transparency and ethical guidelines in the deployment of such AI systems. Section: Discussion. In this section, we discuss our introduction of the AI scientist, the first framework aimed at fully automating the scientific discovery process. We demonstrated its capabilities by applying it to machine learning. This comprehensive system uses large language models, LLMs, to independently generate research ideas, conduct experiments, search for related work, and create detailed research papers. By combining ideation, experimentation, and refinement, the AI scientist seeks to mimic the human scientific process in an automated and scalable way. We believe it is crucial for the AI scientist to write scientific papers, similar to human scientists, for several reasons. First, writing papers provides a clear way for humans to understand the findings. Second, having papers reviewed at machine learning conferences allows us to standardize evaluations. Third, scientific papers have been the main way to share research since modern science began. Papers can use natural language, include visuals, and present code, making them versatile for describing various scientific studies. Until a better alternative is developed, we see training the AI scientist to produce papers as essential for its acceptance in the scientific community. Our framework is adaptable and effectively conducts research in different areas of machine learning, such as language modeling and neural networks. The system's cost-effectiveness is notable, producing papers relevant to conferences at about 15 each, which helps make research more accessible and speeds up scientific progress. Initial analyses suggest that the papers generated are informative and contain novel ideas. We ran our experiments using minimal computing resources, primarily a single NVIDIA H100 node over a week, which shows that scaling up could lead to even higher quality papers. Most of the costs come from using the LLM for coding and writing, while expenses for the LLM reviewer and experiments are minimal due to our cost-saving measures. However, these costs may change if the AI scientist is applied to different scientific fields or larger experiments. To evaluate and improve the generated papers, we developed an automated paper reviewer. While there is room for improvement, our findings indicate that LLMs can produce fairly accurate reviews, comparable to human evaluations. This allows us to assess the papers generated by the AI scientist more efficiently. We found that Sonnet 3.5 consistently produces the best papers, with some even meeting the acceptance criteria for standard conferences. However, we do not expect any single model to remain the best indefinitely, as all leading LLMs are likely to improve. Our work is designed to be independent of any specific model provider. We explored various proprietary LLMs and open models, finding that open models offer advantages like lower costs and greater transparency, despite slightly lower quality. In the future, we plan to use our discovery process to create self-improving AI systems with open models. Future enhancements to the AI scientist could include adding vision capabilities for better handling of visuals, incorporating human feedback to refine outputs, and allowing it to expand its experiments by accessing new data online safely. It could also follow up on its best ideas or even research its own code. Notably, much of the code for this project was written by Aider. Expanding the framework to other scientific fields could significantly increase its impact, potentially enabling experiments in biology, chemistry, and materials science through cloud robotics and automation, as long as it is done safely. Future work should also focus on addressing reliability and verification issues, possibly by linking code and experiments or using automated verifiers to reproduce results. In conclusion, the introduction of the AI scientist represents a major advancement in harnessing AI for scientific research. By automating the discovery process and incorporating an AI review system, we unlock new opportunities for innovation in science and technology. We envision a future where AI plays a significant role in scientific research, including researchers, reviewers, and entire conferences. However, we believe that the role of human scientists will evolve rather than diminish as we adapt to new technologies. While the AI scientist shows promise in building on established ideas, it remains to be seen if it can generate truly groundbreaking concepts. We believe it will be a valuable partner to human scientists, but only time will reveal how well AI can replicate human creativity in moments of unexpected innovation.